Hello, welcome back to our lectures on computational Fourier analysis. Today we actually get to do it. You know, the world seems to be full of two kinds of academics. Those who just like to sit around and talk about how wonderful all this stuff is, and those who enjoy doing things more than just talking about them. Today we're the second part for sure. We're going to actually say and show you how do you do a Fourier analysis on the computer. Okay, so the outline, and we'll probably take a break in the middle because this is a lot of material and it looks like a lot of accounting in the middle, and then when you get done you have this very small, simple formula. You'll never forget it once you see it, and you can apply it all the time. But it takes some while to get there, and you need to understand how we've gotten there. So here's what we'll cover. You can study this. We'll talk about the algorithm, and then we'll talk about the consequences of the fact that we're dealing with real experimental measurements, and that introduces some constraints on the mathematics. So that's a fascinating subject, data analysis, statistics. We'll talk a little bit about that. Then we'll talk about how you use the discrete Fourier transform, the DFT, to synthesize a signal. Okay, so we started off, recall, saying our problem was to determine the number of frequencies and the amount of each frequency present in a signal. And now we're taking that one step further. The way your cell phones work is they may transmit the Fourier transform, discrete values of different spectrum elements, but then they reconstruct that into a signal that sounds very good. It sounds like the voice you're hearing now, in fact. And so that's done by the inverse transform. So we'll talk about that too. That's really why we do this, to compress data and to be able to transmit it digitally. This is all what this is about. And then we'll talk about how you use the same technique for Fourier series. Then we'll give an example of a code implementation. And finally, we'll send you on your way with some very hard problems. No, some easy problems to do, and problems we'll give you the right answers for. So let us begin. Applied math. The pure math, if you want, was the Fourier series. Now we have to try to apply it and evaluate it. So as you see here, okay, we need to evaluate the Fourier transform. That's obvious, okay? We have to do an integral from 0 to infinity, minus infinity to plus infinity, which we never can do on the computer because we don't have an infinite time and we don't have infinite number of points to use. So we have to approximate that in some way, and we approximate that usually by the simplest kind of integration formulas you see here. We sum over a finite number n points. Now I know if we're starting at 0 and we're ending at n, it looks like we're summing over n plus 1 points, but we'll talk about that a lot. So we're summing over n points, and we're using the trapezoid rule because we just replace dt by h. And we do that all the time. That's the trapezoid rule. It's not the very best rule, but it matches exactly what you've done in the laboratory. When you measure a signal, you only measure it at certain values, equally spaced usually, and those are the ones we'll use here. And then we have the exponential here. So that's the usual physics convention. And we have to now approximate this integral. So once we approximate the integral, as you see here, we get a sum of exponentials, here using complex functions, but they're just sines and cosines. And once we have a finite sum of sines and cosines, we have a Fourier series again. So that's what we'll talk about. There, of course, are consequences to follow the fact that we've made approximations here, and that's really the most interesting part of this discussion. So, consequences. But there's also more than just consequences due to having to approximate integrals. There are consequences because we have to deal with the actual data that have been measured. Okay, so the real world constrains us. And we'll simultaneously think of the two problems. Equation 3 gives you the Fourier transform. Okay, our signal is y of t. Its transform is capital Y of omega. And then the inverse transform, or the synthesis, the way we resynthesize the function we started with. So we take the transform, we integrate over that, and if you look at these two equations, you realize, wow, this is pretty nice because they're very much the same equation. Obviously, whatever mathematics we're using for one, we could use for the other. The only difference here is the sign of the exponential. Okay? So the mathematics is going to be the same. Okay. How does the real world constrain us? Now, don't tell me about all the problems you've had in your life. I know, don't want to hear about it now. Outside, maybe, over beer. But the real world constrains us because we've only measured a finite number of signals. Okay? And so we have n, capital N, measurements of the signal. And furthermore, we can't measure continuously. We measure, say, once every second. And so we have discrete times rather than continuous times. But these integrals say, oh, time is continuous and frequency is continuous. Well, that's life. You have to compromise somehow. And the truth of the matter is this: it's not physically possible to ever measure enough values of omega or enough values of time to satisfy these two integrals. We never can do these integrals exactly. So this is a whole class of problems in mathematics known as the inverse problem. How do you deal with both having a finite set of data, not infinite, and how do you then take those data that you know and invert it to get the signal back if all you've measured is the spectrum, or to get the spectrum if you measure the signal for a finite set. Okay? We will present one solution to this problem known as DFT, the discrete Fourier transform. It is a solution to the problem. It doesn't make any more assumptions than the minimum needed to solve for the finite number of data points given. If you don't like the solution, you can do a better job, but it means you have to either put in more data, do more measurements, or you need to figure out a better way to do it, and it probably ends up much the same. So this is about as well as you can do given the constraints. But don't believe me. We'll try it out. We'll do it. So let's talk about the algorithm. We have here our usual stepping routines, diagrams that you've seen when we spoke about ordinary differential equations. Okay? So we've measured time in steps. We start at time 0. We're ending at time capital T, 1 period. So if you have a function, assume it's periodic. And if you know what the period is, you just measure over that period. Why waste your time repeating the measurements over and over again? Okay? So we have a periodic function. If it happens to be a wave packet like we have here, then we're just measuring. We say we start measuring, nothing's happening. We end the measuring, nothing's happening. So that's our period T. Fine. As it turns out, essentially, once we've done the mathematics, the mathematics is going to force us to have this function repeat again and again. So if you don't like it repeating, well, then you just measure for 0 for longer times, then it doesn't repeat till next Tuesday or something, and you're fine. Okay? So that's what we have. We have uniform time steps, uniform, always the same h value. And so each time measurement is index k, happens to be k times h. And then we've measured the signal, or the function, at those times. Rather than saying y of t sub k, much as we did for the ODE solutions, we just say y sub k. K represents time, the kth value. And we let k vary from 0 to n. So that's obviously n plus 1 values, but we only have n unique measurements. But we'll see about that. Okay. The first problem here is because we have finite values of t, the period, we have an ambiguity. We have to resolve that ambiguity. We don't have enough information. So we have to make another assumption. Okay. Furthermore, we have an issue that we've only measured the signal starting at time 0 here and going out to some time capital T. The mathematics wants us to know the signal all the way out to minus infinity, negative times, and then all the way out to plus infinity, beyond where we've done the measurements. We just don't have that information. We could make something up, and mind you, people do, but that's sort of like cheating. You're not supposed to make up data and call it something you've measured. It's really a mathematical assumption. So we have to be careful. We can do this, have to be very careful. So the basic assumption is periodicity. We'll assume that the function we've measured over time period capital T just repeats again and again, like we have here, every capital T. Okay? That removes one ambiguity. Then we know what the function is all the way out to infinity, and we know what it is all the way out to minus infinity. So we've solved that problem. You may not like the assumption, but go ahead, do better if you can. What we'll end up with, the consequences of this assumption we had to make to solve the problem, is that the Fourier transform capital Y of omega is only known at n discrete values of omega, and we call those discrete values omega sub I. I is obviously an index going to go from 0 to n, just like k did up above. Furthermore, because of the mathematics and the assumptions we've made, mathematics being just the mathematics of trig functions, we're going to end up with y of 0 and y of capital N always being the same value. So the reason we said here we have n, capital N, unique values of the function measurement, and yet we start at 0 and go up to n, which is n plus 1 values, is because the first and the last values correspond to the same function value. Because we know the function's repeating, so they're the same. We don't count them twice. We're careful, but we know that's going to happen. Okay, so let's go on. Let's look at the next slide, slide 21. Well, on this slide, we sort of repeat more mathematically just what we talked about on the previous slide. We actually do it. So we look at how the discrete values for the function at the different y values lead to discrete values of the transform at different omega sub I values. Okay? So we have n independent measurements made for the signal y, and that has to lead to n independent values of the transform. It has to? Well, let's say that's the best you can do. If they're independent values and they're good values, then we can't get more out than what we've measured. That's the best we can do. Okay? What are the values of omega sub I? That requires some thought. And it's kind of subtle. It's like a scaling problem. And you have to think about this. And it's often the most confusing part of the discrete Fourier transform. We have this total time t. And what is that? That's the time, what we've assigned, the period of the function over which we've done the measurement. So whether you assume it repeats or not, that's all, we've measured time over a total period of t. And that corresponds to capital N times the discrete time step h. So that's the maximum time we have. And the way Fourier transforms work, they're inverse spaces. So time maps into 1 over frequency, or frequency maps into 1 over time. So omega sub 1, the lowest frequency which we can see in those data, the lowest frequency that's present that we can measure, corresponds to 2 pi over the period t. So as the period t, capital T, gets larger, we can see smaller and smaller values of omega. That's just the way mathematics works. Okay? So that's our limit. And capital T, of course, is just capital N times h. So the fundamental frequency, if you want, omega sub I, thinking of harmonic series and normal modes, which is nice to think of. The fundamental frequency in the data corresponds to 2 pi divided by the number of data points on the interval, divided by the time. That's what comes out of the reasoning. Okay? So we only can get capital N values of frequencies, which means capital N values of the transform. But that's exactly what we always see. We see this spectrum like this, and either if it's a discrete, purely periodic system, we just have finite omegas. But even if it's a wave packet, we do a DFT, we can only get finite values out. So these are the n values we get. Interesting. So either case, anytime you do it discretely, and your cell phones do it discretely, digitally, you just get a finite values. And these are what they are. We know omega 1, that's 2 pi over t. And then we know omega 0, the DC component, is just 0. And then all the other omegas are just an integer k times omega 1. And k, you can say, varies from 0, but 0 just always gives us 0 frequency, the DC component, all the way up to n, which gives us the highest frequency we can measure in the signal. So pretty neat. That's what has to go through. So probably a good time right now to maybe wind back and look at this again, because this is the important part, and I know it's quite confusing often, but this is it. This is how we determine the frequency. This, if you want, is the most abstract thought. What does it mean to have the minimum frequency corresponding to the maximum time? Okay, so now we can get down to the algorithm, and now it's just bookkeeping. You know, the abstract thinking, the hard work is done for us, and we're just going to do the bookkeeping very carefully, watch all the I's and the J's, literally, and the N's and the K's, and when we're done, you should work it out yourself, maybe. When we're done, we'll have a very simple formula. Okay, so let's talk about that. We're using the trapezoid rule. As always, we'll approximate by a discrete sum, we'll approximate an integral of a continuous function. What do we have? First, we have the Fourier spectrum, the Fourier transform, y of omega sub n, integral from minus to plus infinity, and we assume, just as we have any series, the function only will be analyzed from one period, from 0 to t, fine, the only time it exists, and then we just analyze it with a finite sum over that period. So there we have our Fourier spectrum. So our Fourier transform will just be represented by a finite sum always of exponentials. Complex exponentials, so it's just sines and cosines. That's it. Okay. To symmetrize the function, the notation, to make it very neat, and in the end, we divide out by 1 over h. So this looks a little tricky. Y of omega sub n is just the transform evaluated at some frequency omega sub n. We divide by 1 over h, h being the time step, and then we're left with y, what we call y sub n, which we'll call from now on the transform values. So notice that y sub n will have a different dimension than y of omega sub n, and the actual time has been removed, so we'll get a simpler function when we're done, as we'll see here. But consequently, often the exact magnitude of the Fourier transform doesn't matter. What matters are the relative ratio of the different components. And part of that comes about because you'll change the intensity, you change the overall normalization, you adjust the volume. It's the relative ratio of the frequencies that give you the tonal quality, that give you the information you want. And so if there's a term of 1 over h someplace in the equations in front, it often doesn't even matter. So you may find it left out in some books, some notation. I wouldn't do that. I put everything in. Everything I say should be believed. Okay, so equation 10 here gives us our equation for the Fourier transform. Okay. If we look at the next slide, we'll say, how do we actually use the same kind of notation to go backwards? Take a look at the next slide. It's the trapezoid rule for the inverse. Okay. What do we have? Well, we have an integral to do, and we have to evaluate the step size. Okay. So delta omega is, of course, like d omega when we do a continuous integration over frequencies, is what? Well, the smallest omega for our problem is omega 1. So this is, the equivalent of d omega is delta omega, but the smallest frequency we have, which is the frequency step, is omega 1. And that's 2 pi over t, which is just 2 pi over nh. So when we evaluate the integral here, we have dt, we have d omega, I'm sorry. That's going to be replaced by 2 pi over nh, which is right here. Aha. Okay. And we have e to the I omega t, that stays the same. Everything else stays the same. And we have here omega sub n. There's a 1 over h, or an h times y sub n, which will come in and wipe that out, as you'll see. So, but even now you can see, before we write down the final expression, how the trigonometric functions, the basic periodic nature of the trigonometric functions, mean that we have both answers right here. It means that the assumption is that whatever function we're analyzing, our signal will be periodic. So if we repeat the index by capital N, we're going to get a function which just repeats. So every function is periodic. We always get periodic functions. So where we had here a non-periodic function, if we go out far enough, we're going to see it repeating. The other aspect of this DFT is that since the inverse transform is also just sines and cosines, finite sum, it must repeat too. So if what we thought was the Fourier spectrum here, it looks good, but if you go beyond the region here where you start getting zeros, boom, if you keep looking, it's going to come back again. You may think this is crazy, and it may be crazy, but it's just a consequence of the mathematics. However, it has real life consequences, which we'll talk about. So, let's look at these consequences. Okay, so here are the consequences on slide 36. And look at this. We'll talk about this for a while now.